In this tutorial screencast, we're going to look at the synthesis of alcohols from alkenes using two different methods, namely the hydration of alkenes and hydroboration of alkenes. This is going to be an example of Markovnikov's rule in the addition of an electrophile to a pi bond. The two methods we're going to look at are hydration and hydroboration oxidation. In both cases, let's go ahead and start with the alkene propene. Hydration we're going to treat with water and a catalytic amount of sulfuric acid. Hydroboration oxidation is a two-stage process that happens in one reaction flask. The first set of reagents that is added is borane THF with THF as the solvent. The second stage, hydrogen peroxide with sodium hydroxide and water, is then added. So we said these methods are complementary. So what I'm going to do here is write major product. And I'm going to write them down for each case. For the Organic Chemistry 1 Fall 2019 students that are watching this tutorial screencast, for 4 points, please comment on the names of the major products, the relationships to each other, the unique number of carbon signals you would expect in the C13 spectrum, the unique proton sets and their ratios to one another for each of these products. So please pause the video at this point, leave your comment before moving on and watching the rest of the video. The hydration reaction is producing 2-propanol. The hydroboration oxidation reaction is producing 1-propanol. The relationship between these two compounds is that they are constitutional isomers. Let's first look at the mechanism of hydration with water and a catalytic amount of a strong acid to understand how 2-propanol is produced as the major product. So let's go ahead and draw in our hydrogens of the alkene at this point. I'm going to label them alpha and beta. You can see that alpha has 2H, beta has 1H. And so the choice that we have to consider is which carbon, C alpha or C beta, is going to be protonated in the first step of the hydration mechanism. So when you're studying mechanisms, what you want to do is draw out both products so that you can compare the resultant intermediates that are formed. So in this lower pathway, I'm going to show protonation of alpha. In the upper, I'm going to show protonation of the beta. And what is happening at this point is simply the pi bond of the alkene is acting as a nucleophile to be protonated by the hydronium ion, which is the active acid. So if we're to show that for the alpha, so the alpha carbon's getting the proton, we have abstraction from the hydronium. The alpha carbon now has 3 hydrogens. That leaves a carbocation at the beta carbon. And we can classify that as a secondary carbocation. So protonation of alpha leads to a secondary carbocation. Similarly, if we do the same type of analysis, protonation of beta we're going to see that the carbocation then ends up on the alpha carbon, which we can then classify as a primary carbocation. And we know that from our analysis of reaction coordinate diagrams that a secondary carbocation is more stable than a primary carbocation. So if we are to look at how this proceeds over time versus energy, on the y-axis, our alkene is starting at some energy. Since we're forming a carbocation intermediate, we're going higher in energy. So the secondary carbocation is lower in energy. Than the primary carbocation, so that is the preferred pathway, is protonation of the alpha carbon resulting in the secondary carbocation. The remaining steps at this point, water is now our nucleophile. It attacks the Lewis acid carbocation, the beta position. We're now left with this intermediate. That's not quite the final product. We still have to do a proton transfer. We're going to use water to do that. I'm just going to write proton transfer here. That's going to leave us with our final neutral product, 2-propanol. So we can summarize Markovnikov's rule as the carbon bearing more hydrogen atoms will get the electrophile. Because it results in the more stable carbocation formation. So one thing to note in this case, the electrophile is equal to H+. In the next case that we look at, in the strictest sense, it's still a Markovnikov addition. The electrophile is going to be a neutral species, but it is still added to the carbon bearing the most hydrogens, and that reaction is hydroboration oxidation. So in the mechanism of hydroboration oxidation, we want to understand why we get the regioisomeric alcohol as compared to hydration of the same starting material alkene. So in this reaction, we're taking 3 equivalents of propene. We're treating with borane THF complex, and THF is the solvent. And then the second stage, hydrogen peroxide, sodium hydroxide, and water. So first, a brief review of what borane is. So BH3, then this dot THF. What does that mean? So boron is electron deficient. So if we draw the Lewis dot structure of borane, this is what we come up with. We see that it's violating the Lewis octet rule. So it's sp2 hybridized, meaning it has an empty p orbital. That empty p orbital means it's a Lewis acid. And again, a Lewis acid is electron pair acceptor. What is THF? That's Tetrahydrofuran, which is this compound. It's a cyclic ether. It has an oxygen with 2 lone pairs. And so what does that little dot mean? The dot means that there is a dative bond in which the lone pair of oxygen stabilizes that electron deficient species. So that's what borane THF is in terms of the Lewis dot structure. Because the boron is electron deficient, it is the electrophile. And as we said from the Markovnikov's rule, the carbon bearing the most hydrogens will get the electrophile. So as we did before, alpha, beta, the alpha carbon is going to get the boron, the beta carbon is going to get the hydrogen. So let's draw it simplistically at first, and then we'll consider some molecular orbitals involved. Going to draw the propene with some perspective. So now we're looking edge on of the propene. So we know that the alkene has a pi cloud, which is supplying 2 electrons to be the nucleophilic component, or the Lewis basic component in this case. The borane can approach from 2 different ways. And so we want to understand each way and how to predict which one is correct. So in the correct approach, we're going to have the H adding to the beta carbon, the boron adding to the alpha carbon. Then we're going to go ahead and put in that empty p orbital on the boron. And so what is going to happen is a concerted addition of H and B across that pi bond. What that means by concerted is it's happening at the same time from the same face. So H and B add from one face at the same time. How do we push arrows mechanistically? The pi bond will fill that empty p orbital. So we're forming C alpha to boron bond. We're going to break the BH bond, and those electrons are going to come down and bond to the beta carbon. So what is the result of that? We'll keep our stereochemical perspective here. So we have H, then we have BH2, If we remember from our Newman projections, we would say that the H and the BH2 are eclipsing one another. So we know they've added from the same face at the same time. So as we can see from what the final product is, being 1-propanol, we see that the beta carbon has its H already. The alpha carbon now needs to be oxidized, which we're going to transform the boron into the hydroxyl group in the second stage of the reaction. Before we move on to do that, I want to just take a brief minute to explain why the borane does not add the other way to the pi bond. So this is the approach that is not preferred, and it's based on steric hindrance. So let's go ahead and show that under here. In this approach, carbon alpha will get the H, carbon beta will get the boron. We put in the p orbital. And the reason this is not preferred is due to the steric clash between this methyl group back here and the boron reagent. The bulkiness of the borane is going to prevent it from adding to the beta carbon due to steric hindrance. If it were to add that way, we would get the same alcohol as the hydration reaction. But it does not. So let's write a few notes here. This is a concerted syn addition. Of borane across that pi bond. So the reason that we have to use 3 equivalents, as noted originally, is the fact that we're starting with borane BH3 that has 3 hydrogens. We've added 1 alkene. We can do this 2 more times with the same reagent now. So I'm going to write times 2, and what we will end up with is this species. So this is a trialkyl borane. Now what we have to do now to get the OH in there is treat with hydrogen peroxide, sodium hydroxide. And so this is going to generate sodium hydroperoxide. So let's briefly look at that acid-base reaction. We know sodium hydroxide is a base, so hydrogen peroxide is the acid. It has a slightly lower pKa than water of 12. We're going to have the hydroxide abstract a proton. We're going to generate sodium hydroperoxide plus water as the byproduct. So we know this equilibrium is favored towards the product because the pKa of the water is 16. So we shift that totally to the right. So again, any reaction mechanism we can classify things as Lewis acid, Lewis bases, or nucleophile, electrophile. This is going to be a nucleophilic component. Our trialkyl borane is going to be the electrophilic component. We know that because we said before that the boron is sp2 hybridized, so it still has that empty p orbital. So now what is happening in this next step? The oxidation step of hydroboration oxidation. So here's our trialkyl borane. So we have these three propyl groups bonded to the tri-coordinate boron. That's the electrophile. We said we have sodium hydroperoxide as the nucleophile. These electrons will attack the boron. Notice now the negative charge moves from oxygen to boron. It's always good to put in your lone electron pairs to keep track of things. So the boron is now negative, the sodium is the counter ion that's positive. The reason this next step happens is that the boron wants to get back to a neutral species. We know that the carbon bearing the boron has to be bonded to oxygen. So this next step is a 1-2 shift. We're going to break one of these bonds. It's going to attack that oxygen. We're then going to cleave this oxygen-oxygen sigma bond. Hydroxide leaves. Your byproduct is sodium hydroxide, which is fine because you're starting it with it in the reaction medium. So what we end up with is B. This species here, in which one of the propyl groups has migrated over. So that's going to happen 2 additional times with 2 more equivalents of the sodium hydroperoxide, such that we end up with a borate ester. So we're not quite to the finish line yet. What happens next? That sodium hydroxide then comes into play again. And is going to cleave off each of those BO bonds. That's going to free up the alcohols and leave us with this inorganic byproduct borax. So hydroboration oxidation is a 2-stage process in which the alkene first undergoes hydroboration such that the boron is the electrophile, adding to the carbon with the most number of hydrogens. The hydrogen adds to the carbon with the least number of hydrogens, and that's due to minimizing steric interactions. In the second stage, the oxidation occurs with sodium hydroperoxide. The mechanism proceeds through a migration event that ultimately cleaves off the boron-oxygen bonds to free up your alcohol. So in closing, to test your knowledge of this, consider the following alkene: using everything you've learned about organic chemistry to this point in time, consider treating this with the hydroboration oxidation conditions, borane THF and THF, followed by sodium hydroxide, hydrogen peroxide, and water. Predict all the products. Name them. Determine their stereochemical relationships. And determine C13 and 1H uniqueness. So the challenge here is that you're starting with something that is achiral. You have a regioselective addition to either the top or bottom face of the molecule. So that's what you have to consider, is that the borane can add from either face. It's going to add in a regioselective manner, and you'll end up with multiple products that you have to determine the relationship of.